Hey everyone, my name is Nasta Sadati and I'm a PhD student in mechanical engineering at Iowa State University. Today I will be discussing our CVPR paper number 16835, Dimat or Decentralized Iterative Merging and Training for Deep Learning Model. It's a collaborative effort among myself, Min Fan, Nasra Salim, Joshua White, Aditya Balu, Zahan Jian, Chima Heje, and Shumik Sarkar. Dimat is a decentralized deep learning framework that uses recent model merging techniques to improve performance and convergence rate. To explain Dimat, we need to explain decentralized learning and model merging. Decentralized learning is a collaborative machine learning approach where models are trained across multiple local devices or nodes without centralizing data and also distributed computing. Usually requires high communication and computation overhead, practically in large models and sparse networks. Model merging is a popular method for multitask learning by combining different models into a single model without requiring additional training. This is the mathematical representation of our problem. We have n agents, each with the same model and loss function, but with different data distribution, and they communicate through a network topology defined with the mixing matrix. Our objective is to minimize the average loss, which is our global loss. Our goal is to reduce communication and computation overhead in decentralized learning. We aim to explore advanced model merging techniques and enhance decentralized learning adaptability to real-world scenario with sparse and lightweight communication. Here is how our algorithm works. We have n agents arranged in a network topology. Each agent has its own dataset. We start with a pre-trained agent on its own dataset, and then agents are connected using the network topology defined by our pi matrix. We merge the model using activation matching. The agents then train their models for a few epochs, and we merge and train the models again and continue this process. This is the mathematical representation of our algorithm framework, and this is the result of our convergence analysis. We have assumed that our objective function is a smooth and non-convex, and we have both local and global bounded variance. Additionally, our mixing matrix is symmetric and doubly stochastic. The main highlight of our finding is the error band, as it can be seen here, and this is our convergence rate, which is still sublinear. This is our experimental setup. We began our analysis with pre-trained models trained for 100 epochs. We utilized both independent and identically distributed or IID and non-ID CFAR10, CFAR100 and tiny ImageNet datasets, evaluating ResNet20, ResNet50 and VGG16 models. Here we can see Dimat's performance. It's not only converge faster but also deliver exceptional results across CFAR100 and tiny ImageNet dataset. Whether we are using fully connected or ring topologies, Dimat stands out, cutting down on communication and computation rounds. Dimat's performance is notable. It demonstrates effective scalability for a large number of agents and maintain its effectiveness even in non-ID scenarios. Dimat's communication overhead stands out for its remarkable reduction compared to all other baseline, as you can see the result shown in this figure. Dimat is a novel decentralized deep learning framework. It uses recent model merging techniques for increased convergence rate and better accuracy. Comprehensive empirical study demonstrates Dimat's work better than baseline in various settings, supporting our theoretical claims. Dimat shows faster model performance gain with lower communication overhead. Dimat is a practical option for quickly updating large pre-trained models collaboratively. Future research directions include exploring different permutation algorithms and addressing scalability issues with non-ID data distribution in model merging, and investigating the extension of Dimat for transformers and large language models. Thanks for your attention. If you have any question, please reach out via email at nsadati@iowastate.edu.